Welcome. Myself, Mugamarashita, a third sem student from chemical engineering. Today, I will be presenting to you about these following topics, that is entropy generation, lost work, irreversibility, introduction to third law, and numericals related to certain topics. So let us understand what is an entropy generation. How is an entropy generation related in the field of chemical engineering? And why does it matter? So, in chemical engineering, almost every process, such as reactors, distillation columns, heat exchangers, pumps, etc., involves energy transfer and transformation. This helps us to measure and minimize efficiencies in a system. These ideas are deeply connected and help us understand why real processes are never 100% efficient and how we can minimize energy loss in engineering. So, entropy generation is nothing but it is a fundamental concept in thermodynamics that measures the irreversibility of a real process. It reflects the degree of disorder in a system and indicates possible inefficiencies, especially in irreversible process. There are certain factors which affects such as temperature, pressure and friction. So, entropy generation can be defined as the amount of entropy produced within a system and its surroundings during an irreversible process. This represents the increase in entropy of the universe. It can be simply given as Sgen is equal to delta S universe. Let us look into the mathematical expression for entropy generation. So it is given as delta S system plus delta S surroundings is equal to Sgen. So here delta S system is entropy change of the system, delta S surrounding is the entropy change of the surrounding, and Sgen is entropy generated. Types of entropy system in thermodynamics. So in thermodynamics, entropy system can be classified into four different systems, that is open system, closed system, isolated system and adiabatic system. So an open system. An open system allows both mass and energy to cross its boundaries. The given formula below states that dSCV by dt is equal to summation of m dot in into S in minus summation of m dot out into S out plus summation of q dot j by tj plus S dot gen. So here m dot is mass flow rate, S is the specific entropy, q dot j is heat transfer rate at boundary j, Tj is temperature at boundary J, and S dot gen is rate of entropy generation. Next one is closed system. A closed system is the one where mass does not cross the boundary but energy does. And the equation below says delta S system is equal to integration of delta Q by T plus S gen. So here delta Q is heat transfer into the system. Temperature is given as T and Sgen is entropy generated due to irreversibility. So the next type is isolated system. An isolated system does not exchange mass or energy with its surroundings. Thus, the total entropy of an isolated system always increases or remains constant. The given equation is delta S isolated is equal to Sgen greater than or equal to 0. The next topic is adiabatic system. An adiabatic system does not allow heat transfer, but it may allow work or mass transfer. Q is equal to 0 here. And the equation says delta S is equal to Sgen. If the process is reversible, then Sgen is equal to 0. If the process is irreversible, then Sgen is greater than 0. And the next concept is lost work, which is also known as exergy destruction. Lost work is the amount of useful work that is lost due to entropy generation in real process. It can also be defined as the difference between the maximum possible work and actual work obtained in a real process, which is given as W lost is equal to W reverse minus W actual. And when entropy is generated, some available energy becomes unusable. It is directly related to entropy generation and ambient temperature. If entropy generation increases, lost work also increases, which means less useful work output and lower efficiency is obtained. Here, the relationship between lost work and entropy generation is given as W lost is equal to T naught S gen, where W lost is the lost work in joules, T naught is the ambient temperature or surrounding temperature in Kelvin, and S gen is entropy generated during the process, that is joules per Kelvin. We can understand this concept with a simple example. Here, the question says if 1 kilojoule of heat is transferred from a hot source at 600 to a sink at 300 Kelvin. Here, we are asked to find out work lost due to irreversibility. In order to find the work lost, we need to find Sgen. Here, Sgen is nothing but the entropy generated during the process. So, Sgen is given as Q into 1 by Tc minus 1 by Th. We can take Q as 1000 and Tc is given as 300 and Th is given as 600. On substituting these values, we get entropy as 1.667 joule per Kelvin. Then at T naught is equal to 300. So we need to calculate T naught as 300 Kelvin. Here work lost is equal to T naught into Sgen. On substituting the given values, we get work lost as 500 joules. So, 500 joules of work is lost due to irreversibility. Let us move on to the next topic, irreversibility. Irreversibility is the measure of how far a real process deviates from an ideal reversible process. It represents the loss of useful work potential due to inefficiencies in thermodynamic process. It is, in other words, you can also say deviation of real process from ideal reversible one. Here the equation says I is equal to work lost is equal to T naught into Sgen, where I is irreversibility or lost work in joules, T naught is ambient temperature or surrounding temperature in Kelvin, and Sgen is entropy generated due to irreversibility in joules per Kelvin. Thus, greater the irreversibility, more entropy generated and more work is lost. Given below are certain examples in which the natural processes are irreversible, that is friction in pistons and turbines, heat transfer through finite temperature, mixing of two fluids, and non-equilibrium chemical reactions. These effects cause energy degradation, meaning some energy becomes unavailable to do work. Understand with the help of an example. Here the question says a 2 kg mass of water is cooled from 80 degrees Celsius to 20 degrees Celsius by placing it in a large reservoir at 20 degrees Celsius. On assuming Cp as 4.18 kilojoules per kg and ambient temperature T naught as 293 Kelvin. Here we need to first find out delta S system. The formula says M into Cp into Ln by T2 by T1. On substituting the given values in the formula, we get minus 0.186, and on calculating Q, so Q is given as mCp into T2 by T1. Here Cp is already given. We can assume Cp, and T2 is taken as 293 and T1 is taken as 353. On substituting the values, we get Q as minus 502 kilojoules, and heat gained by the surrounding is taken as positive, that is plus 502 kilojoules. And on substituting, we get Sgen as 0.15 kilojoules per Kelvin. Finally, we need to find out I. I is equal to T0 into Sgen. 293 into 0.15 gives us 43.95 kilojoules. So the last topic is Introduction to Third Law. The third law of thermodynamics states that as the temperature of a pure, perfect crystal approaches absolute zero, its entropy approaches zero, that is, limit T extends to zero, S is equal to zero, where S is entropy of a substance, T is absolute temperature in Kelvin. So this law gives us an absolute reference point for an entropy. It also tells us that reaching absolute zero is impossible because it would require a completely reversible process with no entropy generation. Applications. Here are certain applications for the third law of thermodynamics. It is used to calculate absolute entropy values of a system. Important in cryogenics, helps explain residual entropy in imperfect crystals, and provides a zero reference for entropy in chemical and physical process. There are a few numericals which I will be explaining it to you. The first question says 1 kg of water is sealed in a rigid container is heated from 300 Kelvin to 400 Kelvin by absorbing 4200 kilojoules of heat. Calculate the entropy change of water and assume the process is irreversible. So we are asked to calculate the entropy change of water. Assuming M is 1 kg and Q is taken as 4200 kilojoules, and converting it to joules, we get 4.2 into 10 power 6 joules, and T1 is 300 Kelvin, T2 is taken as 400 Kelvin. We can take down the formula delta S is equal to mCp ln of T2 by T1. M is nothing but 1, Cp is 4200 into ln of T2 is 400, T1 is 300. On substituting, we get delta S as 1207 joules per Kelvin. The next problem says 1000 joules of heat is transferred from a hot reservoir at 600 Kelvin to a surroundings at 300 Kelvin irreversibility. Find the work lost. We are asked to find the work lost. Here, first, to find the work loss, we need to find the entropy generation. Entropy generation is nothing but Q into 1 by Tc minus 1 by Th. Here, Q is taken as 1000, Tc is taken as 300, and Th is taken as 600. And on substituting, we get Sgen as 1.667 joules per Kelvin. Using this, we need to find out work lost. That is, work lost is equal to T0 into Sgen. On substituting, we get work lost as 500 joules. Here, 500 joules of work is lost due to irreversibility. Importance in chemical engineering. In chemical engineering, these ideas are vital for improving efficiency. First, in reactors, minimizing entropy generation improves conversion and reduces energy loss. In heat exchanger, smaller temperature differences mean lower Sgen. In distillation and separation, reducing irreversibility cuts down energy cost. Overall, lowering entropy generation supports sustainability and green engineering.